Well, we want to welcome everyone to, this is our fourth week, isn't it? All the way up to week number 4. Well, good. We're glad all could join us tonight. We're going to continue on where we left off with chapter 3. We're going to finish off chapter 3, and then we're going to get into the first part of chapter 4 tonight, which is, we'll be covering a lot of some of the mathematical stuff, and that's why the expert is going to be teaching that. I'm just a bean counter. If it's not add and subtract, no.
I'm sure you do.
So anyway, third-party traffic, that's where we left off last week. And so what is third-party traffic? So it's basically, we're sending messages on behalf of someone else. And Lee's going to yell at me because I'm getting in front of the podium.
Stop that.
So he's going to tell you to stop it. I will try to stay back here. I'll try to be good. Okay, so you're sending messages, also known as traffic, on behalf of somebody else, right? And it's someone else who is not an amateur radio operator. Okay? Now, foreign governments, they have an interest in limiting this because it bypasses the normal internet. They don't have the control over it. So they also passes telephone. It also passes postal systems. So they don't like this, right? But it could still happen. But the FCC recognizes the value, and it wants people trained to provide effective emergency communications. So if you think about it, when we have emergency communications, we need to be able to get messages out. You know, if there's an earthquake in Syria, right? And people are trying to get messages out to somebody, and their communication systems are dead. What are they going to do, right? Ham radio will get those signals out. So they're going to want to send message. You know, it's like, you know, I'm going to say, Brian, can you send a message to California? I've got relatives over there. They can't hear me. I can't call them. And Brian has someone in California he can send a message to, and they could call him. So we could get a message out in an emergency. So the FCC wants that to happen, right? And Randy has a comment.
I was monitoring third-party traffic this morning with the devastation in Mississippi. There was a couple of guys talking, wondering about one of our fellow ham radio operators. Couldn't get a hold of him, so they're trying to route third-party traffic to get some information out of it.
Yeah.
It's real-world stuff.
It is. It happens. I mean, if you look at that devastation that happened down in the South just this weekend, right? Yeah. It just completely wiped out complete towns. They're no longer there. They're gone. And people trying to get that information out, that's so important. And so that's why the FCC recognizes that, and we allow third-party traffic. And so third-party messages, it's also called passing traffic, okay? So traffic is that message that you're passing along. Okay, so third-party traffic must be exchanged between amateur stations operating under FCC rules, okay? Can't be commercial. It's got to be non-commercial. And the messages either need to be personal or unimportant or relating to emergency and disaster relief, okay? So it's not like you can be sending a message that says, you know, I'm a company, right? I can't send a message for a company. It's got to be non-commercial. I can't be sending a message that's of an important nature, you know, unless it's an emergency. So it has to be personal or unimportant. You know, I could say, you know, Bob's got a great haircut, okay? It's personal, maybe. Unimportant, maybe, right? But you see the difference? Okay. And the third party is the person or entity on whose behalf the message is being sent. So in my example earlier, Brian would be sending the message on behalf of me. Now, this would be saying that, you know, I'm not an amateur radio operator, right? I can send my own message. But if I was not an amateur radio operator, I could go to Brian and say, Brian, can you do this for me? And he could do that, okay? That would be passing that third-party traffic. And it can be an organization. So if we have the Red Cross, let's say we have the Red Cross down in Mississippi, and they're trying to get messages out. They will often use amateur radio to get those messages out, and they will take that message to an amateur radio operator and say, I need this message to get out. Okay? We're an Aries Club, which is an amateur, help me out, Lee.
Amateur Radio Emergency Service.
Amateur Radio Emergency Service, okay? In the event of an emergency, we have a tornado comes through St. Cloud. We can be called upon to do just that. We may be serving the Red Cross. We may be going to that, they may come to us and say, hey, we need your help. Stearns County, they're a serve agency. We can receive calls from Stearns County, and they say, we need you, and we need you to do this in regards to radio communication, and we'll do that. We'll pass that third-party traffic, okay? Make sense? Okay. And that third party doesn't need to be present. So when I get a hold of Brian, I don't have to be there. Brian can do that without me being there, okay? So for more information, you go to the ARRL.org site, third-party operating agreements, okay? All right, we're already up to practice questions. Good, good, good. Here we go. Which of the following would disqualify a third party from participating in stating a message over an amateur station? The third party's amateur license has been revoked and not reinstated. The third party is not a U.S. citizen. The third party is a licensed amateur. And the third party is speaking a language other than English. What do you? Hey, I think you're right. Yes. Okay. And what type of messages for a third party in another country may be transmitted by an amateur station? What do you think?
C.
C. Only messages related to amateur radio or remarks of a personal character or messages relating to emergencies. And when it says remarks of a personal character, we leave Rick out of the mold. Okay? Unless we're saying Rick is a great guy, you know, that kind of thing's good. And he is. He is. Okay. So we have third-party traffic. Then we have traffic that is prohibited. Okay? Or it's restricted. We have restricted communications. So one-way transmissions are not permitted except to practice code. Randy can send one-way transmissions when he's practicing his code, you know, Morse code, that is. But if I was to get on there and say, oh, this is N0JFY and welcome to our morning radio show, that would not work, okay? Can't do that. Can't retransmit a broadcast except for weather or propagation predictions from the U.S. government stations, as long as it's occasional, okay? You can do those weather reports and propagation as long as it's occasional. You're not doing it all the time. But you can't rebroadcast. So if I've got the radio on in the background or the TV on in the background and I'm on the radio, I better turn it down, right? Every once in a while you hear somebody on the radio and they've got something on the background and you hear them, oh, wait a minute, I got to go turn this down, okay? And that's the right thing to do. Okay, codes intended to obscure meanings of messages are prohibited. So if I want to send a message to Howard and I don't want anybody to know what it is, and Howard and I have a code. So if I say, Howard, it's an A14327, would anybody else know what an A14327 is? No. Can I do that? No, I can't. All right, here we go. Some more practice questions. Which of the following transmissions is permitted? Unidentified transmissions for test purposes only? No. Retransmission of amateur station signals by amateur station? No.
C, Charlie.
C, Charlie. Occasional retransmissions of weather and propagation forecast information from U.S. government stations, and I would say, yeah, that is correct. Okay, which of the following one-way transmissions are permitted?
B.
B, transmissions necessary to assist learning of international Morse code. That is correct. And what are the restrictions on the use of abbreviations or procedural signals in the amateur radio? Only Q signals are permitted. No. They may not be used if they may be used if they do not obscure the meaning of the message.
Yeah, B.
Okay. They are not permitted? No. Only 10 codes are permitted. B. B is correct. Okay, when is it permissible to communicate with amateur stations in countries outside the areas administered by the FCC? Only when the foreign country has a formal third-party agreement filed with the FCC? Okay, I'm hearing a couple of yeps and a couple of nopes.
It's B.
Okay, when the contact with the amateurs in any country except those whose administrations have notified the ITU that they object to such communications.
Yes.
That is the correct answer there. Yeah, they have to notify the ITU that they don't want it. Okay, otherwise it's allowed. Because I remember when I first was reading that, I thought, hey, they got it. If they have an agreement, what's the deal? Well, they have to specifically say we do not want it, and they communicate with the ITU. Okay, when may a 10-meter repeater retransmit the 2-meter signal from a station that has a technician class control operator?
D.
Only if the 10-meter repeater control operator holds at least a general license, and that is the correct answer. All right, now we're getting into rules and standards. Good amateur practice. This is a good one. Good amateur practice. This is being nice on the radio, okay? That's essentially what it is. Not all procedures are covered by the FCC Part 97 rules. Not everything is written down, okay? They don't have to command us in all things. You know, it doesn't have to be in the rules. Amateurs themselves set day-to-day operating standards, although the FCC reserves the right to rule on what is and isn't good engineering and good amateur practice. Remember that piece, okay? Especially the last piece of this. Yeah, that doesn't work. This does. Okay, right here. Good engineering and amateur practice. The FCC can state that, okay? Randy, I like your pointer. Works good. Okay, many publications are available covering these practices, including the ARRL Handbook, the ARRL Antenna Book. And let's talk about output power for a minute. We've talked about this a little bit in our past conversations. General, advanced, and amateur extra are limited to max transmitter output of 1,500 watts PEP, peak envelope power, on the HF bands. Okay? 2, Q signals for indicating power level. And you're going to hear these if you're on HF. You're going to hear at least one of these all the time. I don't know that I've heard the other one all that often, but QRP. What's QRP? Low power, right? Low power. 5 watts. 5 watts. Okay? QRP. Low power. So it's 5 watts or less. Now QRO, increased power, or I'm using high power. I'm using that 1,500 watts, fellas, and I'm blasting all over the place. You can hear me everywhere. QRO. QR outrageous. Okay, 2 max power restrictions on HF. 200 watts PEP on 30 meters, which is your 10 megahertz, okay? 30 meters, 10 megahertz. Remember that from our conversions and between frequencies and meters that Penny put together. And 100 watts PEP with respect to half-wave dipoles on 60 meters with max bandwidth of 2.8 kilohertz, okay? 2.8 kilohertz, 60 meters bandwidth. Okay. Practice questions. Who or what determines good engineering and good amateur practice as applied by the operating rules?
FCC.
The FCC, that is correct. I told you it'd come up in a question. What is the maximum transmitting power on an amateur station they use on 10.140 megahertz?
A200.
A200. And that is what meters?
30.
30. Yep.
Yeah.
Exactly. Okay. What is the maximum transmitting power of an amateur station may use on the 12 meter band? C, 1500 watts PEP. C, 1500 watts PEP. What is the maximum bandwidth permitted by the FCC rules for amateur radio stations transmitting on USB frequencies, upper sideband frequencies, in the 60 meter band?
A alpha.
A alpha, 2.8 kilohertz. Correct. And which of the following limitations apply to transmitter power on every amateur band? A. Only the minimum power necessary to carry out the desired communications should be used. Okay? The minimum to carry out the transmission. Okay? Some of that, you may need some more power, right? Some of that you may only need 5 watts, 10 watts to carry it out. All right. And what is the limit for transmitter power on the 28 megahertz band for a general class operator? C, 1500 watts PEP. Correct. And what is the limit for transmitter power on the 1.8 megahertz band? D is correct. What measurement is specified by FCC rules that regulate maximum power output? D. Peak envelope power. Spread spectrum. What is the maximum PEP for spread spectrum transmissions?
B.
B, 10 watts. That is correct. You guys are good. What is QRP operation? High power? Low power. You got it. It's B. All right. We'll talk a little bit about digital. FCC rules for digital transmissions are primarily concerned with the bandwidth of the transmitted signal. So you're transmitting a signal. They're worried about how much bandwidth you're taking up. If you have too much bandwidth, you're going to splatter all over everything, okay? They want that limited. They want that bandwidth limited. And it's tied, bandwidth is tied to the symbol rate and signal events per second. And it's covered by those sections in the FCC regulations. As the size of amateur bands increase with frequency, faster, wider signals are allowed. At 33 centimeters, 902 megahertz, and above, there is no limit except for the band edges themselves. You can't cross the band edges. You got to keep it within the band edge. So you're at a very high frequency, you've got a wider bandwidth. There's no limits. Okay? So here is a table that shows what we've got going for us. Okay, so in 160 through 12 meters, the symbol rate is 300 baud, and the bandwidth is 1 kilohertz. So you got to keep it at 1 kilohertz at 300 baud symbol rate. 10 meters, you can have a symbol rate of 1200 baud, still 1 kilohertz. Yeah, you know what I mean. 6 and 2 meters jumps to 19.6 thousand baud and 2 bandwidth. Now we're bouncing up here to 125 meters and 70 centimeters. We get 56 baud and 100 for the bandwidth, and 33 centimeters and above, there's no limits. Okay? Does that make sense? Or have I confused myself?
Something to memorize.
Something to, basically, this is one that you're going to kind of have to just kind of throw up here in your head. Okay? Okay. So there are new protocols being introduced all the time. Okay? We got FT8. It's not been around all that long. It's a few years, right?
About 5 years.
5 years. Okay, before that it wasn't. There's one that's going to come out next year. I don't know what it is, but it's going to come out. It's going to happen. So the FCC recognized the need for amateurs to receive and to understand signals, that they must be balanced with the benefits of the innovation. As things change, as things are innovated, the FCC knows that that's happening, and they understand that there needs to be signals and things need to be changed. So this is why the FCC requires that the technical characteristics of the protocol be publicly documented before using it on the air. It must be publicly documented before using it on the air. Okay? Must be publicly documented. Just kind of keep that in your mind. It's an important piece. Oh, yeah, it'll be in the questions. What is the maximum symbol rate permitted for RTTY or data emission transmission on the 20-meter band?
Delta.
D delta 300 baud. You are correct. So 300 baud goes down to what? 160 to down to 12. Okay. There we go. Okay, so what is the maximum symbol rate permitted for RTTY or data emission transmissions at frequencies below 28 megahertz? D, 300 baud. Below 28 megahertz. 28 megahertz is what? 10 meters? So when you go below, we're talking frequencies now, not the bands. Okay, remember that. They go opposite directions. So the frequency for the 12-meter band is 24. 24. Okay? So 24 is less than 28. And you're down to 14 for 20, right? So the boss is laughing at me again. She does that. All right. I'm going the wrong way again. Here we go. Okay, the maximum symbol rate permitted for RTTY or data transmitted on the 125 meter or 70 centimeter bands is what?
56.
56 kilobaud. Yes. And the maximum transmission on the 10 meter band,
C.
1200.
C1200. Yes. And the maximum permitted on the 2 meter band,
19.6.
Yeah, B.
B 19.6. Yes. And what must be done before using a new digital protocol on the air? C, publicly document the technical characteristics of the protocol. Told you, you want to remember that. You guys did good. And that's the end of Module 3. And I need to switch over here to Module 4. We're going to talk about power and decibels. We're going to, you recall Ohm's law from your technician training? That picture look familiar? It apparently looks familiar.
But you know what?
And I'm going to turn it over to Miss Penny.
I'm going to start with decibels, and the easiest way to understand decibels, I think, is to go over exponents first. Okay, and do you all? Okay, where is my? Oh, here we go. Okay, so have all of you had math up to the level where we talked about exponents? I mean, I can review more if I'm not sure where everyone is. But, yeah, I mean, did you learn about exponents in math? Do you remember that?
Years ago, I went to school.
Oh, okay.
Over 40 years ago.
Okay, all right, well, I'll just do a review. It's on the page that I gave you, but, you know.
You stick some laughs.
Okay, so it's like any number to the 0 power is 1. So here, this is equal to 1, but it could be 5 to the 0 power equals 1. Any number, 636 to the 0 power equals 1. Yeah. So, okay, so that's anything to the 0 power is 1. Okay, and then but the exponent really is just, okay, and then like 10 to the first power is just 10, because it's just 110. I mean, okay, and 10 squared is just 10 times 10. Is it coming back? Okay, 10 to the third power is 10 times 10 times 10. Pretty, and then so on. 10 to the fourth power is 10 times 10 times 10 times 10. Yeah, 4 of them. And then, yeah, so that's pretty easy. Okay, and so we'll erase that. And there's also something, well, we have negative exponents too, but it's not, but all that means is you just take the reciprocal of it. So like 10 to the negative 1 is just 1 over 10. 10 to the negative 2 is just 1 over 10 times 10, which is the same as 1 over 100, you know. 10 to the negative 3 equals 1 over 10. I'm sorry, can't read my writing very well, but just 3 equals 1 over 1,000. Okay, it's pretty simple, right? Is everybody following me? I mean, okay. All right. Now, did you know the exponents don't have to be whole numbers? You can have, well, okay, I'm going to use the number 9. You can have 9 to the 0.5 power. But 0.5 is the same thing as square root. And do you remember what square root is?
3.
Yeah, the square root of 9 is 3. The square root of any number is, yeah. It'd be 3 times 3 is 9, right? So if 9 to the, what about 10 to the 0.5? That would be the same thing as square root of 10. But it's not going to be a whole number, is it? You know, but it will be just a little bit bigger than, it's actually 3.16. I mean, if you get out your calculator and push the square root. Okay, so I just did that. Okay, so there you have, I made a little chart. If you look at it right here, I have starting with 10 to the 0 power on one side. Remember, anything to the 0 power is 1. Then I have it on the end, 10 to the 1 power, that's 10. And then in between I have 10 to the 0.1, 10 to the 0.2, 10 to the 0.3, 10 to the 0.4, so on, all the way up. And, well, like so you may think, well, what is 10 to the 0.1, what does that even mean? 10 to the 0.1 is 1.26. But if you were to multiply, this is the 10th root of 10. Like if you were to do 1.26 to the 10th power, that means multiplying it by itself 10 times. You would get 10. Because it, anyway. So.
Okay, run that by again.
Oh.
10 to the 0.1 is 1.26.
Yeah, if you have a calculator that has exponents on it, you can do 10 and then push the exponent button and then do 0.1 and it will give you 1.26. And then if you, so that is actually the 10th root, you know. You could take 1.26 to the 10th power, which means multiply it by itself 10 times, and you get 10. 10 to the 0.3 power, if you have a calculator, is 1.995. Or isn't that just practically 2? Because each decibel increase, like a 1 decibel increase is 10 to the 0.1. You know, 2 decibel increase is 10 to the 0.2. 3 decibel increase is 10 to the 0.3. Well, this is just a really quick and easy way to figure out what a decibel is. Like if 3 decibels, do you remember in the technician class when it said like every 3 decibels represents doubling the volume level or the power level of where you were?
Yeah.
Okay, well, this is where it comes from. This is practically, that's what it means. It's sort of equal to 2. And this is why. It's because this is 3 decibels.
You're just rounding it off then.
That's the factor. This is the number that you multiply. So if your power level is 5 or 10 or whatever, you just multiply it by 2.
Okay.
You get that. That's okay.
And then if you have there.
Okay, then what? Where did I? Well, anyway. Oh dear.
You want me to kick him out?
Well, I don't know. Well, it's just you have a power level of whatever it is.
Yes.
But then when you want to increase it like 3 decibels, you multiply it by 2. Because,
Okay, there we go.
Okay.
Now you bring me back.
okay, well, what part didn't you get?
Don't ask.
Okay, well, because 10 to the 0.3 power, remember, was equal to 1.995,
Yes.
which is approximately equal to 2.
Yes, I got that.
Okay, right. So a 3 decibel increase, to figure that out, you just take 10 to the 0.3 power. This is it. And this is the number that you multiply by whatever power level you're at.
Okay, so I'm at 5 decibels.
Okay? Yeah, right. So, yeah, that's true. Okay, 5 decibels.
And I want to increase it by 3 decibels.
Do you want to double it? Yeah, that's right. 3 decibels will double it. Yeah, right.
So if I increase it by 3 decibels, I'm doubling it to 10 decibels.
Yes. Maybe I just didn't follow what you were saying. Okay. Okay, does that look like decibels? Okay, this is 3, yeah. Yeah, you're 5 decibels right here, that's true. Okay. You want to increase it by 3 decibels.
We multiply it by 2.
Right. All right. Anyway. Okay, well, anyway, but any increase of power, like 1 decibel
Yep.
is 10 to the 0.1. And looking at the chart, what is that now? It's at 1.26 or something like that? Yeah, 1.26, because I calculated them before. Okay. So yeah, so you're at 5 decibels, and you want to
Increase it by 1.
increase it by 1 decibel, you'd be 1.26. And then get out your calculator. Yeah, 6.3 or something. Okay. Anyway.
So this section can be very confusing, as you can definitely see. So I can get easily confused.
Okay.
That's just me.
Well, I didn't follow you. Okay.
But this section can definitely get confusing on the test. So what you want to do is you want to, do your best. Some of this stuff you're going to want to memorize. Some of it, if you can calculate it, you're okay doing that way.
Okay.
Which will be better. But don't get too hung up on the math stuff, because there's a lot of other questions within the general section, the general test, that if you actually missed all the math questions and you got
You'd probably
the other
still
stuff
pass.
right, you're gonna pass.
Right. If you're doing a decibel decrease, like you're going down, then you do a negative exponent. So like 10 to the negative 0.3 is, it's about 1/2 or 0.5. And you would expect that, right? Because remember, 3 decibels, when you're going up, it doubles, and when you're going down, it would be going down by half. The question is, what decibel change represents a factor of 2 increase or decrease in power? It is 3, right? And we just talked about that, right? Because,
That works.
I mean, this is practically 2, okay? So yeah, if you're going bigger, you have a 3 decibels. If you're going up, and if you're going down, you're doubling. And if you're going the other direction, you're doing it in half. So, yeah. Okay. What is the factor of 2 increase if you had a starting power level of 6? Factor of 2, 3 decibels. What is it? 12. Yes. And what is the factor of 2 decrease if you have a starting power level of 6? What did you say?
3.
3. Yes. Right. For a starting power level of 100, was power level after 3 decibels loss? Do I have that next? Okay. So what would be a 3 decibel loss? If we're starting at 100, what? Remember, what is 3 decibels loss? It's the same as 0.5. So it would be half, right? And what is half of 100? 50. Okay, right. So what would be the power level after a 5 decibel loss? So 10 to the negative 0.5 equals 0.316. Okay, and I made it a little more challenging. Instead of doing 100, we're going to do 80. But it's the same thing. You just multiply 80 times 0.316.
252.8.
Yeah, which is 225.28. So that's this would be a 5 decibel loss. Okay, so the last question on the bottom says, how does a signal that reads 20 decibels over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S meter? So the only thing you need to worry about is 20 decibels above. One signal is 20 decibels above the other. So how much more is that? So remember so you have 20 decibels would be 10 to the what power? Remember, you just move it over 1 decimal spot, it would be 10 to the 2.0. And so that's the same thing as just 10 to the second power. So what is that? 10 to the second power is 100, right? Because it's just 10 times 10 equals 100. So yeah, so the answer is D, it's 100 times more powerful. So that one turns out to be actually pretty easy.
That's right out of the question bank?
Yes, it is. It's G4D05.
Got it.
We did learn about these equations, voltage equals current times resistance. And I still remember when Jeff was teaching this, I was thinking, oh great, just throw formulas at us, And then what made it even more confusing is that voltage, the abbreviation is an E, so it doesn't even match. Current is an I. Resistance is an R. Okay, that made sense, the R, but I was like, why? So, yeah, right.
Well, the E is for electromotive force. That's the pressure that's pushing the current.
Yes.
Current is an I because Faraday used C for capacitance before, what's his name? Ampere came up with a theory of current. So that's why we had to use something different than C for current.
Yeah, that makes sense. But yeah, when I looked it up, I mean, it was just like you said, E for electromotive force. And, or I sometimes just think of it as just energy. And the I, back when the scientists were still figuring out what electricity was, back in the early days, there was the French scientist, he called it, say, intensité courant, which is intense current. So, this is intense current. And then, resistance, okay. And then we know that voltage is measured in volts, current in amps, and resistance in ohms. And when I was trying to understand this, because I knew that that I really needed to kind of find something to relate it to help me. I mean, memorizing it isn't that good. I mean, sometimes you have to do that. But I wanted to have it become a part of me, so I was trying to relate it to something, and I thought, well, I wonder if current is like a bike. Okay, this is just me. And my legs are like the voltage, and the road is the resistance. Okay, so this was my own little analogy. I came up and, it made sense. My legs have to be powerful enough to move the bike and deal with whatever the road has. I mean, if the road is nice and smooth, then all I have to worry about is moving the bike. But if the road is bumpy, uphill, rocky, whatever, it's going to make it way harder, to move that bike. So this is the way I was able to make sense of it, as I just thought of it like that. And it worked. So, okay. And then there's another formula. And once you learn both of these, they're kind of like the two main ones, because most of the others are just kind of derived from these. So then we have power equals voltage times current. Power is measured in watts, and again, voltage in volts and amps, for current. This thing right here is in here, isn't it? So, I mean, if you could substitute current resistance, put that where voltage is, then you'd have current times resistance times current, which means current is in here twice, isn't it? Power equals I squared times R. That means there's two currents and one resistance, if you want to think of it that way. Another way, so that's another derived formula. Another one that is used more often is okay, so we have voltage, and then we try to substitute something for the current. So we have voltage equals current times resistance, but we can, if we want to have just the current on one side, we can divide each side by R, because it makes it still equal, right? I mean, when you have an equation, if you do the same thing to both sides, it's still equal, right? And R divided by R is 1, so it beats I times 1. So that makes it I equals E divided by R.
Just like up on our thing above.
Right, it is up there, yeah. Okay, I equals E divided by R. So I is current, remember? So, and then E is voltage, so that's divided by R for resistance, okay? Or another way to say it, I'm just going to do that for power. And then this is voltage times voltage, right? So that's voltage square divided by resistance. Okay, so that's another formula that is used. The first question is, how many watts of electrical power are used if 400 volts of direct current is supplied to an 800 ohm load? So we can just use this equation right here, okay? So how much voltage do we have, according from the question? 400. And what is the resistance? 800. Okay, so what is the number that would need to fit right there? We have 400 equals something times 800. 800. 800 times 400 is 0.5. Yeah. Hey, teacher. Yeah. Yeah, I mean, this is the number that fits, right? So we just figured out what the current is. Okay, so we figured out what the current is, but now we need to know the watts. That's the power, right? So we'll go over here. So if we know what the voltage is, we'll put that in right here, 400. And the current is 0.5. So what is 400 times 0.5? Yeah. Okay, so that's the B answer right there. Okay. Did everybody's fine with that? Okay. All right. All right. Okay, the next one. How many watts of electrical power are used by a 12-volt light bulb that draws 0.2 amps? Okay. So, what is the voltage on here from the question? 12, right. And what is the amps? Or the current? Yeah. 0.2. So 12 times 0.2 is 2.4. Yep, right. So, guess we all got that one. That was not too okay. All right, now we'll go on to the next one. So yes, all of the ones on this page involve direct current. Yes, I mean that's why it's titled that. Okay. The next question: how many watts are dissipated when a current of 7 milliamperes flows through a 1250 ohm resistance? Okay. So yeah. So first we've got to figure out what the. Okay, so let's start with this equation over here. And what is the current from the question? 7 milliamps. Okay. And what does milli mean?
0.007 amps.
Yes. 0.007 milliamps. That's how we write that down. Okay, and then what is the resistance from the question? Yep. Okay, and so do you want to figure out what the voltage is? Multiply that together.
Calculator.
Well, I've got it written down. Should I just tell you what it is?
61 milliwatts.
Yeah, 0.007 times 1250. Oh, I did bring some extra calculators if people need them, but looks like you've already got some. Okay. Okay, so what's that? 0.007 times 1250?
61.
Well, I'm just doing the voltage right now. What's this thing? Yes. Yeah, 0.007 times 1250?
8.75.
8.75, yes. So now that we know the voltage, because we want to know what the watts are, that's power. Okay, so now we can do the voltage, 8.75. And we already know what the current is, right? 0.007. Multiply those two together, 8.75 times 0.007. Okay.
Times what?
8.75 times 0.007 is the current. So we figured out the voltage, remember? The voltage and the current.
0.06125.
Yes. 0.6125 is what that is.
61 milliamps, or milliwatts.
Yes, and it is, yeah, it is, because this is tenths, this is hundredths, thousandths, so, yeah, it'd be approximately 61 milliamps. That is right.
Milliwatts.
Okay, so now we're going to talk about root mean square. And would it be helpful if I just talked about what root mean square is?
Please, good start.
Okay, or give an example of it. Let's see. Well, I'll just read what I have first. I say, it's the formula scientists came up with to find an equivalency between direct current and alternating current. I mean, we know the difference between those two, right? Direct current is just straight direct, and alternating current is the waving up and down. Yeah. The formula is really simple. You know, it's just 0.707 times the alternating current, so that. But I thought maybe I would, I mean, just the idea of root mean square, I thought maybe I would give an example of that. So, like, just take the root mean square. Let's like say we have these 5 numbers, 1, 2, 3, 4, 5. Okay. Now, if you were to add these up, what do they add up to?
15.
15, right. And if you were to take an average, there's 5 of these, right? So 15 divided by, excuse me, 15 divided by 5, yeah, I was anticipating. 15 equals 3. So that's the average. So, but the root mean square, it would be, you would take the square of each one of these. So 1 square is 1, right? 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25, and that equals 55. And this divided by, well, anyway. So, and then we have 5 of these numbers, right? Take the average of that, that's 11. And take the square root of this. And that is the root mean square is 3.316. So you can see how it's just a little bit bigger than average. Simple formula is just, you know, the voltage of RMS is 0.707 times the voltage of the peak.
Peak of the sine wave.
Yeah, the peak of the sine wave. Yeah. So that means, well, it means, well, okay, so you have the sine wave going like this, right?
Like you have above your head.
Right. But it would just be this part of it, you know. You're just doing half of it. That is the peak. Now, when they talk about voltage peak to peak, they're talking about from here to here, you know. But right, but this formula is just peak. It's just half of it. So. Okay, so let's do the questions. What value of an alternating current signal produces the same power dissipation in a resistor as a DC voltage of the same value?
RMS.
RMS, yeah. That's kind of the definition, is we're trying to get an equivalency between RMS and between the AC, alternating current and direct current, right, RMS value. Okay, so this next one we get to do, I'll leave that up there. What is the RMS voltage of a sine wave with a value of 17 volts peak?
12.
Yeah, 0.707 times 17. Well, that's the peak voltage. And then 0.707 times 17 is 12.019.
Yeah.
And then the closest answer is 12, right? Okay, so yeah, that's not too hard. Yeah, just, okay, that one isn't. Okay, the next question. What would be the RMS voltage across a 50 dummy load dissipating 1200 watts. So 1200 is equal to whatever this RMS voltage is square over 50, okay? So we have this by itself, let's multiply both sides by 50. Okay, so 50 divided by 50 is 1, so this is just RMS voltage squared equals 50 times 1200. 50 times 1200 is what?
Big number.
60,000.
Yeah. Yeah. 60,000. And then this RMS voltage, okay? Okay, this is RMS voltage squared. But if we take the square root of both sides, see, then this is just the RMS voltage. Equals the square root of 60. And what is the square root of, 60,000. What is the square root of 60,000? 244. Okay.
I was gonna leave the 0.3 on.
244.948. And that is really close to the B answer, 245. Okay, so that was root mean square. Okay, the next page, peak envelope power. We first need to compute the RMS voltage. And then, use the regular electricity formulas. And then for unmodulated carriers like FM or CW, the peak power and the average power is the same. Now, why is that? Does anyone, should I tell you or does anyone want to tell me? I do know, but does anyone want to? Oh, okay. All right. Okay, so the peak envelope, do you have the slide that shows that? All right, but you see how the amplitude varies, So it's not, yeah.
It's not perfect.
Yeah, it's part of it's, narrow and part of it's bigger. Okay. So that's a modulated, that's like amplitude modulation, And frequency modulation is the other way, right? It's modulating the frequency. So with frequency modulation, it's going to be even, all the way across. It's not going to be like that. So that's why, and CW also will have the same amplitude all the way across. So that's why they're called unmodulated, because they're not going to vary like that. What is the output PEP from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter output? The root mean square is 0.707 times the peak, but in the question it tells you what the peak to peak voltage is. It says the peak to peak voltage is 200, so what would the peak voltage be? 100, yeah, it would be half of it, right? Because the peak to peak is from the top to the bottom, and we're just talking about just the top part, right? So to get the RMS voltage, we just do times the peak would be 0.707 times 100. And what is that? 70.7, yes. So that is the voltage, the RMS voltage. Now, and then remember the power, we're going to use this power formula right here as the voltage square over resistance. So 70.7 squared. And the resistance is what? 50. And that will equal, if you have, or should I just give you the answer? Unless you want to compute it, 70.7 squared over divided by 50 is equal to
0.1. Right. 707. Oh, never mind.
70.7 squared. I'm sorry if my writing isn't very clear. Let me.
Divided by 50.
70 point,
100.
yeah, not, I got 99.968, yeah, right, yeah. Oh, my writing is just terrible, okay. Okay, 99.9698, which is practically equal to 100, so yeah, that's the answer. Okay, the next question. What is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? Okay, so we know that the RMS voltage is 120. And we know that to compute that, we had to multiply 707 times the peak, whatever the peak is, right? So first we'll figure out what the peak is. So,
707?
yeah, 0.707. I'm just using this formula up here. So this is the voltage that we got from the question. And then this is just the formula, 0.707 times the peak. So I'm going to divide both sides by 707. So that that becomes 1. So the voltage of the peak is 120 divided by 0.707. Does anyone want to? Okay, that's the peak voltage, but the question is asking for the peak to peak. Yeah, so you multiply it by 2. Okay, so yep, this is the answer then. Okay.
So we've gone through a lot of calculations tonight, a lot of information. You know, peak envelope power, voltage, current, you know, a lot of stuff. I don't know, my head hurts, okay? I'm sure that yours are probably something like that as well. But there's a lot of calculations, but don't get hung up on the calculations, okay? They're important, yes, they are. And as you work through them a few times, you'll get this down, okay? And as you work through them and with the problems, that will make them even make a lot more sense. So I would encourage you to do that. I encourage you, as I know many of you are working through hamstudy.org, as you walk through those questions, you know, try to work them out with the formulas, and you're going to find yourselves way far ahead. Especially when you get out and trying to figure out, you know, do I have enough current going through this? Or is my voltage, are my capacitors enough to cover what I need? Or am I going to have a bad system when I get it put together? So you want to figure these things out. So next week we will we'll wrap up 4A and get into 4B, and we've gone through a lot of it, and I appreciate all your answers. I mean, you're keeping me thinking. She's keeping me thinking, and I keep failing, but it's all good. It's all good. We learn as we go. Any questions tonight? All this fun stuff that we've been covering. Anything? Anybody has any questions? If not, thank you all so much for coming tonight.